I'm still seeing like, okay, sorry. Welcome to our class this wonderful morning. And it's my hope that our good Lord has kept you, has sustained you, and that you are in good shape and mood to start our semester. So it's my hope that, allow me just to mute that because I was just monitoring the voice. If you can hear me well, you can confirm in the chat section. And I don't know, the audio seems to be muted. Our semester morning. So it's my hope that, sorry for that. Allow me just to mute that because I was just monitoring the voice. If you can hear me well, you can confirm in the chat section. And I don't know, the audio seems to be muted. Our semester morning. Oh, I don't have to hear myself here. Sorry for that. Allow me just to... Okay. So let me get it. Good. So you can also confirm for me if you can hear me well. You can just indicate in the chat whether my audio is okay. Before we start off, I know when we are starting the first class, usually we have some small hitches here and there, but I believe with time we are going to adjust and become okay. And also for the sake of good visibility, with time I'm going to switch off my video. So for those who don't know me, my name is Dr. GATHIMBA, structural engineering and civil engineering, JQuat. Maybe some of you have met on the streets, maybe not, but now I know if you meet one another, you'll be able to understand or say hi to me. It's a short course that we are having and relatively new, so I don't expect much problem in this one. One of the advantage of this course is that it's relatively independent. Usually in our course we talk of theory of structures. You started with theory of structures 1, 2, now you are in 5, and you found that maybe you couldn't start theory of structures 2 before you handle something in 1. But the beauty about these theory of structures, which we are calling Introduction to Finite Element Methods, is kind of relatively independent, not built up on others. You just need to have a basic understanding of structural mechanics, some mathematics here and there, computation. That's the beauty of it. But the thing about it now, being a relatively new kind of a concept being introduced, it's borrowed so much from other things, not on theory of structures, like from mathematics. We're going to do a lot of solution using numerical methods. We're also going to solve so many matrices. So I'm kind of just preparing you so that there'll come a point where we need to refresh on some of these array courses that you did maybe in first years. You learned about how to solve maybe simultaneous equation using the matrix method. So we're going to do that. My office, of course, is in ELB 112, 113. If you know the Dean Civil Engineering office, you can just visit me there when you have the query. But of course, you have to book because we are not always there. Now, though we call it theory of structures, in a nutshell, the content is on a finite element methods. And this is kind of a new method of solution or analyzing structures. Remember, theory of structures is kind of analysis of structures, so that now you are well prepared to be able to do the design. Yeah, because a mistake that may happen or happens to many is like you become well acquainted with the design softwares, but you have not done adequate analysis of a structure, such that the results that you get from the design of the software or from the software, you just digest it. But you should be able to critique. Like, for example, knowing like if let's say you are designing, right now you are doing design in, I believe is in concrete. So you're going to know the issue of L over D allowable. So allowable deflection. So even if you use a software, whatever type of software somebody uses, and then you find like this is a span of 6 meters, and you know what the L over D allowable is for such kind of a member, then even if the software gives you some imaginary values, you're always going to question the result, or like see the result, because you have the understanding from the analytical side, analysis of a structure. Now, you've tackled, or you've been introduced to different methods. You started with the determinate structures, like you were dealing with the trusses, and you're able to use like a method of resolution and joints. You're able to use like graphical methods, method of sections. Then you came to indeterminate structures. You are introduced to different method, Castigliano method. You are also, I'm just giving an example of different methods that you have used to analyze structures, maybe analyze beams, analyze at column, analyze at truss. So this is just another method that we are introducing called the finite element method. It is a relatively new method. It's not been there for the past one, maybe in less than a decade. That's when it was introduced. And you'll find a lot of literature in this, and many fields have adopted this. And because it's wide and deep, so what we are going to have today is kind of an introduction. Not today, actually, in this course, is an introduction, right? So that you understand the concept bit by bit, so that later on, because even most of the design softwares that you're going to use, they employ this concept of finite element methods of analysis. So you'll have understood the basic concept. So before we start, I would just like to welcome you to this platform and tell you the schedule of this course, the way we plan it. You see, things happen for a reason. When COVID came, we never used to have these online things. And we were pushed, or you are forced to innovate, to be innovative. And you realize that we have, or I came to realize that we have a lot of content that we give or we develop, but it's just evaporating into the thin air. The many hours that we do the lectures, and then they just disappear in the thin air once we have finished with that class. But then I realized we could help you as well as help other peoples at the past, help other peoples in different locations. And we are building a global community of scholars. So that's why you find like where we are now, we are on YouTube. Why? Because we are going to have this recording, leave it here, you can refer to it in future. Your brothers in the second year, third year, as they come by, they can refer to it. I've been surprised. We started last year, and then you get comment from people all the way from US and UK, and they say, Marim, this one has been helping me. Can we get this and this? And we feel happy because you are contributing towards a body of knowledge. You could make this your home, because one of the things is that there is a lot of material in this channel that we have been posting over time. Some tutorials that we did last year, but one when there was COVID. And even if you're going to go back physical, because we're going to have some classes physical, others online, maybe in the future you might go fully physical, but this will remain a home whereby we can have a digital repository where people can always come and have some references. So as I'm saying, can make it your home. You need to book your spot by subscribing and also sharing these videos and even archiving them wherever you want to use them later. And it's not only in structural engineering that you have materials here. You're also going to fifth year where you'll be having projects. And we also have encounters and engagement with different peoples in fifth year. So you can always be looking at those presentations, how they have been improving their work, so that when you get there, you're not starting from scratch. So it's a good repository that you can be able to get a lot of materials in. Okay, that being said, let's stick to our content for now. Again, I mentioned too is that one, there is a chat area where you are registering your attendance. You can also ask your question there. Usually when the class is going on, we can go through it together. But I also, if you want to ask a live question, of course, I share the link with the class rep for the Zoom, because I'm in Zoom now. So you can always ask a question, live question, if you feel like typing it out is not very convenient or is not very clear for you. But usually to avoid, I know you have encountered this in other platforms where there is a lot of interaction, interaction, but at the same time with the interaction, there is interference because the bandwidth and the communication is that. So usually I prefer, we have the question in the chat section now, then we answer them. Towards the end, then we have a session of engagement. That's when now I'll share the link for YouTube, for Zoom. The class lab group, they have a group whereby I share with them. They can share with you now, and then if you feel you want to join me here, you can join and ask questions. But you'll also be live, so that the question you ask here, the other people listening on the other side can always listen in and also contribute. All right. So this is the content of our course for today. And that being said, I'm saying, let me just go off the video. I was told last time that sometimes it hides some content. So we always continue improving. So allow me to just go off the video, and then I can make this full screen so that you can see clearly. Okay. So this is the content. Okay. Sorry for that. Yeah, this is the content of our course. So we're just going to have a short introduction to FEM, and this is theory. I like people understanding the theoretical part. Even if usually in structures, the question will be calculations, but we need people also to understand why we're doing this, what's this, right? And that being said, we are going to have a short introduction to finite element methods and how it's applied in structural analysis. Then we are going to go to calculations proper in matrix analysis of structures, where we are going to see application of this method in solution or in analyzing plane trusses. We always start with a truss. I know you have heard trusses so many times, because truss is a very simple structure for practice, for hard calculations. Usually when you start going to beams and frames, especially frames, you find like manual calculation it may become an uphill task. So we always start, usually, not always, but usually you find many books, many texts, many lectures in analysis, they use a truss as an example for demonstration purposes. Then we are going to see, once we see for the plane trusses, 1D element, kind of 1D structural element, we are going to see for two-dimensional continua. When you start going now to solid element, 3D. So we start with 1D, 2D, then 3D element. So what is expected of you from this course? At the end of this course, you should be able to follow the standard procedures of the finite element method. The beauty about this method is that there are procedures standard, like kind of 7 standard. Whether the problem is so humongous, it's a big structure you're analyzing, a multi-story building, but the procedures are there. It's kind of a standard. So whatever you can be able to do for a simple structure, the same procedures that you follow are the same procedures that you follow for even that mega structure that you're going to analyze using this method. So you should also be able to apply the finite element method to analyze trusses, beams, and frame structure manually. Get this right, manually. And then later on, we are going to go to usage or adopting using relevant softwares. And these are software for analysis in finite element method. And there are those software, in as much as I say, some of these design softwares, they employ the finite element method of structural analysis. You also realize that there are those softwares that are custom made for finite element method of analyzing structures. And we are going to see a number of them like Abacus, Adina, ANSYS, right? But you're also going to see some design software, even as simple as Procon. When you analyze like a slab, they use the finite element method of analysis. But those are generally designed softwares, not for analysis of finite element methods, right? So you should be able to handle a few cases using manual method, then we go to software, usage of softwares. Finally, you should be able to apply and explain the principle of FEM to continuous two-dimensional problems. This one, we might even go to three-dimensional, but using softwares. So once you understand the principle using 1D structures or structural elements, then you'll be able to move to software, and then we can do for 2D as well as for 3D, okay? Now, our methodology is as follows. We are going to have lectures blended weekly for 2 hours. Maybe every week is for 2 hours. And then, of course, I know there are 3 hours for tutorial. So in total per week, we have 5 hours of learning. So what happens is that physical interaction or interaction with the lecturer, whether physical or virtual, by the lecturer, is about 2 hours. You can go for 1.5 hours, you can go for 2.5 hours, based on the content that you're having for the day. The other 3 hours, which I believe for us is on Monday, you use it for your practicals because you're going to have computation or numerical analysis using softwares. And then you also use it for your assignment and tutorials. And that's why in second part, you're having interactive tutorials. Usually I can issue a problem in class. I expect it to have some people answering or giving some possible solution in the next class. So usually when we leave and you have those questions, you discuss it amongst yourself. And then if there is a challenge, then that's where now I can come into and help you work it out. But as I do so, it means you also need to see how much you have gone into it, how much you've been able to attempt with handle the problem. Finally, there'll be the laboratory work using the software. Of course, we may have other presentation from time to time. If we can have some specialists can come and teach us on some of these softwares, because of course, generally you don't know everything. Yeah, there are many softwares for finite element analysis. Like now, I use Abacus. We may get somebody else in the field who can use ANSYS and come and just show us the demonstration. Remember the purpose of this learning, the guide that we give. What we do in class is like giving you a guide. We are training to be engineer. So if you can get many people, you don't have to know one software to the depth, to the core at this stage. If you're introduced like, how can you handle this software? Can you, like, for example, in design, now you have time as a student, you should be able to touch or have a feel of different softwares, how to use a master series, how to use SAP 2000, how to use TAD Pro. Even if not detailed, can you be able to design maybe a typical beam? So that when you graduate, and if you find yourself working in a consulting firm, you don't know which software they use. So they might be using, you may have trained so hard on Procon and you are an expert, but then when you go to that company, you realize they are using Revit structural, combining with a robot. And because you never looked at it, you find like you are in a totally new grounds. So at this stage, it's good to have a feel of this. And of course, I'm not saying you should not go into depth with one, but make sure you experiment with the different softwares. And that's why I'm saying, like, we may have a case whereby we are bringing somebody to show us different softwares. Of course, the ones that I know, the extra that I don't know, then we can bring another person to show us them. This is how we assess the course. Of course, you know this. The first part is obvious. You know that exam constitutes 70%. Of course, the second one is also obvious, but the distribution is, you should look at it clearly so that you put weight to each and every one of it. So you're seeing the pass mark is 40% for us, right? And for our case here, sorry, something is happening with the chart. Huh? So for the CAT is 15%, and then we have the practicals 10%, assignments 5%. These are our main reference textbook. Of course, we should be able to get other materials. This one, maybe I was using them 3 years ago when I was preparing the content. Actually, this content was prepared 2016, but we have been updating it as we go by. But what I'm saying is that this course or this topic, finite element method, is rather a new concept, and you find so many literature, so many people with interest in it. So it's very easy to get material for learning in this course. So let's start with just understanding what is finite element method. And even before I get to what we have in our notes, I can just give you an example. So let's have something like a circle. Okay, you have a circle like that. Then usually you have what we call the dimension, right? You are shown the diameter. Is it the diameter or the radius? Okay. So you can be able to get the radius of this. So if this radius is given as r, okay, we should be able to obtain, so this is given as r. You should be able to obtain what is the circumference. Circumference, which is 2 pi r or pi d, okay? Now, this formula is analytical, right? This formula in itself, it applies at any point. So at any point in this structure around this body, we be able to calculate the circumference. This is a regular shape, a circle, rectangle, triangle. We have analytical formulas. These formulas, analytical formulas, they have been derived or they have been obtained mathematically, like from first principles. Okay. Now, consider a case whereby we have a still kind of resembles a rectangle. It's not a polygon, but you have something like this. Okay. And then we want to calculate what is the circumference of this body. How do we go about it? Of course, if it was a polygon, maybe even a polygon, you don't have a direct. Do you have a direct formula? Maybe not. So if you use, somebody may come and say, why don't we just assume it or approximate as a rectangle or as a square, as a circle? Why don't we just approximate as a circle? Okay, maybe that's not from the center. We approximate as a circle, maybe. Okay, something like that. And then we get, what is this, the radius, then we can get a value for circumference of that circle. That is approximation. It's not exact. Now what happens for the finite element method? For this kind of a problem, we subdivide. We want to calculate the radius, I mean the circumference. So we subdivide our work into a number of segments, like that is a straight one. So you say this is element 1. We subdivide it to another one, 2, maybe up to there, 3, 4, 5, like that. Okay, 6, 7, 8, 9, 10, 11. So we can say in total, we have subdivided our shape into 11 elements. And in fact, now I'm introducing the word element. Now, this body, initial body was continuous. Even initially, the blue line, if you can see the blue line here, yeah, the blue, you pardon my color, in case I say blue or pink and it's magenta. For men, of course, we know us with colors. So this one now, it was a continuous body. But for us now, we are saying we can get the circumference by just getting what is the length, like a length of element 1 plus length of element 2 plus all the way until we get the length of element 11. Okay. So with that, then it means we have been able to subdivide or to break down a continuous structure into discrete elements. Now, you're seeing where I'm trying to introduce now the terms. First, we have the continuous body. Okay, so we have the continuous body here. Then, for us to be able to analyze it, maybe getting I'm just using a simple quantity that every one of us knows, the circumference. So we are saying for us now here, we can obtain for that irregular body by breaking it down or discretizing it. Discrete, discrete, it means it have definite. Continuous body, maybe it's continuous, of course, as the word says, is continuous. Discrete is that it's composed of small defined element, clear defined element, like the one we are saying, this element 1 is from this point to this point. So this point, this element, at this point, the elements are joined together. At this point is referred to as the node. They are joined together at the node. So we have node 1, we have node 2, which define this element 1. which is running from node 1 to 2. Then, of course, we have another node. So nodes are a point of intersection of different elements. So this is what constitutes finite element. Like a continuous structure, we discretize it or we break it down. Once we break it down, we obtain or we analyze a single element. We break it down using finite elements, create defined element. And once we get this element, we can be able to analyze for this small body. Like we can be able to get what is the length of this small body, which we call it a finite element, element 1. Then for the overall structure, we need to assemble back, because once we break down, we are saying you take it separately. This is element 1. This is element 2. This is element 3, like that. Element 4, separate. Then whatever it is that we wanted to determine, here we are saying circumference. So circumference will be given by the length of this one. To get the circumference of the whole body, we assemble. So it's a summation of the lengths all the way I from 1 to 11. Okay, summation of those lengths Li. So no matter what, even if we go now to our structure, if we wanted to know what is the deformation, we just need to break it down our structure, and then we analyze for a single element, what is the deformation or what is the stress in that element. Then we assemble for the whole structure. And now you can see why we are starting with 1D element or with 1D structural element is that it's easy to handle an element that is running in one direction or one dimension. Because if it was a plate, if this body, you remember now I'm just talking of a circle which is open. So if it was it was solid, this is hollow circle. So if it was solid, then it means we would have to subdivide this body into so many elements, okay? And then we analyze for these different elements. So you can see the number of elements increase. So now we are having not one dimensional element which was aligned, but now we are having 2D element. Then we analyze for each individual element. Then we can assemble back to obtain the behavior or the performance of the overall body. And this is what we call the finite element method. We do not use analytical method, and we are going to see why analytical method might not be applicable. We use a numerical analysis method. Numerical, if you remember, I know you did numerical analysis. Numerical method, these are approximation methods. Like when you use the trapezoidal rule, Simpson rule. I don't know, that's where we talked about, was the Rungakuta method there? I don't know. But what we are saying is that I remember when even in your Simpson, your SMP tables, you have these the formulas for the trapezoidal rule. So if let's say we have a curve like that, you want to get the area under the curve, then you subdivide it into different ordinates. So of course, what you are doing here is approximating, because we join this by straight line. And then whatever you get is an approximate area under the curve. So this is a numerical method. Our finite element method is a numerical method. It's an approximation method. That being said, now and understanding where we are running from, so we can define finite element method as a numerical method that we use to solve problems in engineering and mathematics. Of course, they give an approximate solution to a given boundary value problem. Now, I know you might start running when we talk of the boundary value problem, but you're going to see what's that. Look at this body, and I know you have seen it in when you are talking of strength of materials or mechanics, and you talked of the stresses, the principal stresses, maybe in a small body, in a structure. Then you extract a body, then you start analyzing the different stresses. And these are principal stresses like the sigma ZZ, like you're talking of sigma YY, sigma XX. This is a stress in direction of Y in direction Y. But we also have other stresses that are in other directions. To simplify what I'm saying for those people who might, maybe they kept their books away, they forgot after the holidays. What we are saying is, consider if you just have, you have done concrete cube test, okay? You have done concrete cube test. So we apply a load here, okay? And then we obtain this area. Let's say we are talking of 15 centimeter by 15 centimeter by 15 centimeter cube. So you can get what is the strength of the block by just saying the load applied, of course, divided by the cross-sectional area, right? But remember, once you advance, especially when you move to master's level, you talk about advanced structural mechanics, you realize that as you apply this load, this structure or this body, let's talk of this concrete cube, does not experience only compressive stress. It's also experiencing tensile, because as you compress, the fibers, these are pulling apart here. And that's why you find failure by cracking, because it means there was a tension occurring. Okay, so it means as you apply compression stress, there are also other stresses that are experienced on the body. So if you take a small element, a small body, we talk of infinitesimal body here, then we start analyzing. That's a small body that we are talking of here. Then we start looking at the principal stresses that are on that body. And remember, in this body, we have not even shown, we are talking of, if of course we are talking of the stress in direction, on a plane Z in direction Y, then we start talking of the shear stresses that are occurring. Now, you see now to describe stresses in this body, right? We have, of course, you know, stress is force of area. You can get the strain, which is stress is equal to Young's modulus times strain, all those relations, which are analytical. Now, to analyze this kind of a problem or a body, what happens is that I hope I did not bring both of them together, but I wanted you to first forget about this part. So ideally, we use, or this problem is constituted by a number of partial differential equations, which is the first part that we are getting here. Okay, partial differential equations. Then we introduce boundary condition. Of course, these are the advixities. Like if you have a body, let's say a cantilever there, which is built in here, then you apply a load either here. So we have a boundary condition. We know at this point, there is no vertical movement, there is no horizontal movement. U of V is equals to 0. So we apply these boundary conditions, and then we use the finite element method. We convert all this, which was complicated analytically. If you use the PDE, partial differential equation, it was a complicated formulation. But now, once we introduce the boundary condition, we can use the finite element method to convert our structure into simple linear algebraic equation. The complex equations are converted to linear algebraic equation in this format. Y is equals to mx plus c. Then you can be able to simply solve this equation and then assemble together to analyze for a whole structure. This is a technical definition of what is happening. Like, it gives an approximate solution to a given boundary value problem. That's what I'm explaining here. But in a nutshell, what we are saying with the simplified expression that I gave at the start of the previous slide is that for a structure which we might not be able to use analytical method, or we don't have an analytical equation, like the circumference of a circle, if it's an irregular shape, then we discretize, use boundary condition, convert that to simple linear algebraic equation, and then we can be able to solve for our structure. Okay, so far I hope we are okay. If not clear with you, you can always chat, so that as we continue, I will be looking at any comments that we are getting along the way. Okay, good. Now, let's get maybe before we move to that FEM proper, let's get further understanding of this. Like, why do we need to have somebody disturbing us here? Don't worry about that. We always encounter this. Even when you go to Zoom, there was that which we were, I don't know what we are calling it, Zoom bombing. That's why I'm always very careful with my Zoom. Anyway, why do we need FEM? You may ask yourself. Why do we need FEM? One, we may have structures with complicated geometry. Like already we have seen, for a simple circular member, or maybe let's say circular shape, we can just use empirical, not empirical, analytical expressions to solve for whatever quantities that we want to determine. But if I'm going to disable the chat area for a while, because I believe there is somebody who is out here to mess with us. So allow me for a while to deactivate the chat. I hope it will go. I just hope it doesn't take long. I will just continue because these are what we call okay. All right. Now we are saying for let's say for a circular body, like this, we talk of that we can be able, or we are able to get or to analyze, to calculate the circumference using analytical expression. But then we also said if we have an irregular shaped body, then in that case, the geometry becomes complicated. Number two, you are used to cases whereby you have maybe simply supported, let's say like this is a beam, simply supported beams. We may have cases whereby we have maybe one head is fixed. Remember, when we have more unknowns, more degrees of freedom restraint, our problems start becoming a little bit complicated. Now you can imagine when we have a structure, real structures, of course, it's constrained on this head, maybe it's constrained on this head, it's constrained on this head. Maybe on here we have a roller support. Maybe on this head now something is happening. So boundary condition may also become complicated, such that the methods that you are used to in your other method of structural analysis may become may not be feasible for application in our analysis. Again, you may have very complicated loading and material properties. Remember, when you are analyzing for the beam, usually you are told like E and I is constant, or even E is constant. E is Young's modulus, which represents the material characteristic. Yeah, remember, stress is equals to strain times Young's modulus. So where you see the value E, if you're given, it represents the material characterization. And then if you're given I, it represents the geometry. Because the stiffness, rigidity, flexural rigidity, if it's a beam, or stiffness of any member is composed of, or its carries. The stiffness is contributed by the geometry of a structure and the material of that body, material properties. Okay, and that's why you find if this is concrete, the stiffness or rigidity will be different if it was just a plastic pipe, because of the material. Even if the cross section is the same, maybe the dimension are 200 by 200, but the materials are different, so the stiffness varies. So this component which you are usually given in an equation or an exam setup, for example, the E and I, the Young's modulus, and the Young's modulus, and the I, the second one, the moment of inertia, they represent a stiffness. So usually, when you are told E is constant, it means the material characteristic of this body is constant. But you'll find bodies which are composite, that the materials vary. Like you find at this point, maybe the material is the material here in this section A is different like in this section B. So you find like the methods that you have been using for analyzing that kind of a structure now can't work in this particular case. Or even if they can work, it means it's difficult or it's very tedious employing those methods. Okay. Now, if you look at what we have just did, we can be able to Now you can see we can be able to use our structure if our method. Sorry for that. There's somebody slapping me here. We have never had this kind of nagging problem. Eh? So if this material is different than this other part, okay. So what we are saying is that we can analyze our structure differently. First, because we said we discretize or we break it down into different bodies. So we break down, so we can be able to get whatever quantity we want to determine. By quantities, I mean if you want to know what is the deformation. And here I'm just general, because I'm showing like a typical, this could be a plate element. So you might be talking of those people in thermodynamics, heat. So you want to know what are the temperature. If I heat at this point, what temperature after 5 seconds, what will be the temperature this part? If you're talking of shells, there's a load that is applied at this point here. So you want to know what will be the deformation at the location, maybe 5 meters from this end. So basically, it's a general thing that I'm considering in this part before we specialize now on structural problems. So what we are saying is that this part, we can be able to, because now we are able to discretize our structure, and then we have individual element. Like this element now you separate it. This element is like this. Okay, you separate this element. Now you can analyze this element individually, and then to get the behavior of the overall structure, that's when we talked of you assemble back the whole body together. So this is now why FEM comes into play, because of these 4 general cases: complicated geometry, boundary condition, complicated loadings, and material property, or different material properties. So now you understand why did we need to introduce a different method? Why couldn't the others that we have learned so far work, right? Now, let's move ahead and see these structures or these shapes. They are regular. They are not complicated geometry. So basically for this one of them, like for a circle, you have the formula for the area, the formula for the circumference. If it's a sphere here, you have the area, the volume for the formula for the volume. Same case for like a cube or a cuboid here. But now when you're dealing with real life structures here, these are like mechanical parts. So you see they are complicated. And that's why now you need to analyze each part independently, because you may find like even these cases may have different material property. Maybe the outer one is made of steel. The inner one is made of a certain alloy of steel, so on and so forth. Closer home here and closer to our area of specialization, because we are in structural engineering, you look at this structure. For those people who have moved around, I know they have seen this structure. This is outside the University of Nairobi, right? And this structure is made of concrete. You can imagine, at one point you'll have to analyze this structure to make sure that it stands. So this is not your typical beam. This is not your typical column or frame. The geometry itself tells you that something needs to be done. Okay, so that's why now finite element will come into play, because now how do you model this using the normal method that you have encountered? So even if you model it in softwares, then those softwares are going to analyze, because you find like the geometry is changing, the boundary condition may change, and at the same time they may want to use maybe reinforced concrete on one side, they use maybe bricks on the other side. So the materials are varying. Okay, so these are the cases that we are saying finite element method comes in handy in analyzing these kind of structures. So if we try to compare between the finite element and the analytical method, because most of the methods that you have been using were analytical, we see there, of course, there are advantages and disadvantages of either of the method. And one of these is to know the definition. Like the analytical method, if we can take these as a, let's kind of, we are comparing 2 items. We are comparing 2 oranges, because you can never compare orange with bananas. So we are saying this analytical method, by the definition, if this side we have the analytical method, and then this side we have the finite element method. And remember, we can say finite element method or finite element analysis, the same thing, FEM or FEA. So this analytical method, because we have a clearly defined expression, what you find is that we have a mathematical expression, and this expression will give us correct or yield the value of a desired unknown, and it's varied at every location. Okay, but for our finite element method, because we said it's an approximation method, and I go back to our circle here so that you understand what I want to make, the statement I want to make with this. So we said if we have a body like this, okay, irregular. So if this is composed of different elements, and we are trying to approximate this circle, for instance, so you find where it meets the circle is only at the nodes. So the exact solution will only be exact at the nodes, but anywhere else is just an approximation. So that's the other difference. This is exact throughout all points, okay, throughout any location in a body. While the FEM method, it will yield approximate value of unknown at discrete location. The only exact value will be obtained at the node. Remember, we are not trying to approximate using finite element method. We approximate for a regular body. We are talking of an irregular body. Okay, so when we have an irregular body, okay, remember the finite element, we are going to see about the sizing. They do not necessarily have to go up to that end. So you may have to arrange your work into many finite elements, okay, such that you find like at one point, the element is not lying on the boundary. It's like this. There is always a short maybe gap or difference between the actual and the approximation. Now, number two, for analytical method, so for analytical method, we solve for the entire system in one operation. When we solve the partial differential equation or the ordinary differential equation, like the one I gave in the second slide, we are solving for the whole structure at the same time. But for the finite element method, we realized, like we discretize, we break down our structure into finite elements. Then we analyze for those finite elements, and then we assemble together. So you can see there is a difference. Analytical method solving for entire system. Finite element method, we solve for individual element, then we assemble. Of course, design for finite element method, we can employ when the design is a little bit more complex and the accuracy requirement is a lot higher. But you find like finite element method comes in handy in cases when structural, the normal analytical structural method of analysis cannot work, and we gave the reason why. So of course, we know the FEA is an approximate method. The answers or the solution that we get are approximate. So how to improve the accuracy of the approximation is by refining the element size. Because the bigger the element size you use, the more or the diversion or the divergence of the results from the actual solution. Of course, there are many applications of finite element method. In our case, but you realize that like this one is mechanical engineering, structural engineering, in fluid flow, heat transfer, electromagnetic field, soil mechanics, acoustic. But for us, we are going to dwell with this because, of course, we are in civil engineering, structural engineering. We are going to dwell with static and dynamic and linear, non-linear cases. Okay, but first we start with dynamic cases in structural analysis. So, of course, you may get some textbook. You find like they are difficult for your understanding because maybe they are tailored towards people in mechanical engineering who are interested in heat flow. Maybe in electrical engineering, who might be interested in the issue of electromagnetic field. Okay. So, but for our case here, when we stick with structural analysis, now we narrow down. Now you know when you go to look for this literature, it will be interesting, like to look at different books and you see, oh, this one maybe not very good for my use in a structural analysis, so let me go for this particular case. Okay. So we are narrowing down. Then, all right. Okay, I was on a call with the chairman. So what I said is that we have narrowed down to we employ in structural analysis. This is where we are going to concentrate our work on. So what are the advantages of the FEM method of structural analysis? Of course, these are quite clear from what we have said. Our method can be able to handle irregular shaped bodies quite easily. Okay. So again, you can be able to enumerate this. You say that it can handle irregular geometry very easily. Then we can also handle general load condition without difficulty. So any load condition can be handled by our method here. Then, of course, if the material is composed for composite materials, materials or model bodies that are composed of several different materials, because for the element, we use equation and we evaluate them individually. Again, we can be able to handle different kinds of boundary conditions. Okay, so you are not now afraid of the boundary condition. Again, we can be able to include the dynamic effects. I know you maybe have been studying about the static analysis, but it's good to understand that we also look at the dynamic effects for our structural analysis. We can do those easily in finite element method. And we can also be able to handle nonlinear. Most of the analysis that you have been doing were linear analysis. You are restraining yourself within the elastic range where Hooke's law apply. But for this method now, we can go to nonlinear behavior of a structure. Okay. So you can see the advantage of this method over what you have already handled in previous cases or in previous courses. So what's the basic concept of a finite element? The basic concept is that you take a complex body, you have a complex object, then through breaking it down or discretizing, you create separate simple elements that you can do simple analysis on. So basically what we have in the real world, we have a complex body. We simplify using a physical model. Then those physical models, which we now discretize, we have the physical model will be small finite elements connected at nodes. And then for those now finite elements, we use mathematical models. Okay. Very simple algebraic equation to analyze those simple finite elements. And then we can, what we call the meshing. We have the mesh model. The overall body, when you are bringing it back, it will have been subdivided into many elements. So in this case, when we are talking of, let's say we are talking of a body, which is not 1D, let's talk this being a plate. Let's ignore the weakness. So it means we have subdivided this body into many finite elements. Okay. Maybe we want to analyze the deformation of this plate at the center of the midpoint. In this case, it could be a slab anyway. So at this point, if you look at it, it looks like a mesh. So discretizing and subdividing our body, when you bring it back together, the different elements, we talk of meshing. Okay. So you're going to get this term in many codes, meshing. Okay. And just to bring you to speed, all these softwares or all these programs, even the program that you are using now here, they have a coding behind it. They have the coding language. And for the one that we talk of the finite element, you talk of the finite element. Let's say I take an example of Abacus as a typical analysis software. Then it means you would be able to then the software, you have to understand that when it's analyzing, the coding behind it is Python. Okay. So you may go to others, they are using MATLAB, there are others, they are using Fortran. So for any software, even the Word or the Excel or this Microsoft Office, there is the coding language that runs behind that. Okay. Why was I saying that? I was talking about the meshing here. Oh, it was just by the way so that you understand. If you want to go deeper, maybe in this area, you find like programming, having a knowledge of programming comes in handy. Okay, but as I said, this being introduction, we are just doing it kind of at the very, very basic level, without having to take you or to push you to those programming things. This will be at analysis or at an advanced stage as we continue. Okay. All right. Now, let's move to, there's somewhere I wanted us to stop today, so that as you digest this, or maybe we can just finish this small part for theory, so that next time we're now doing the calculation. This is an illustration of the concept of the finite element or finite element analysis, just the basic concept of how we're going about here. We have our body here. We divide it in smaller pieces, which we are calling element, which we said it's meshing. So these small pieces, we refer to them as element. And these elements are joined together at the nodes, okay? At the nodes. These are the nodes where the element come into contact, they are joined together. Now, you separate. You have meshed, then you break it down, what we refer to as discretizing. You make it discrete. The continuous body, you make it discrete, so that you are dealing with an individual element. Then you perform element-wise calculation. We perform analysis per element. Then we assemble together. Once you have done the analysis for the single element, you can assemble together, and now you can be able to recoup your quantities. Like here, you're talking of deformation. Obtain, like, for example, deformation, you at node for this entire domain, because you already obtained the deformation for individual element. You assemble together, and you can be able to derive for the overall structure. So this analysis, I know you might have seen this either in a textbook, either in papers, either in software, if you have ever used, where now people do analysis and then they present their result in terms of contours like this. So behind the workings, this is what's happening in the software. You define the mesh. This is what you do for yourself. You define the mesh, but then this calculation and assembly is done by the software. It runs at the back of the software or whatever you're not seeing, and then you're able to get to visualize the results like this. Okay. So we have different types of finite elements, which we can categorize into three categories. One is 1D line element. It's just one direction. So this one, there's no depth, there is no width, just one line. And this one, we use it to analyze what we call kind of the spring, truss, beam, pipes, etc. Then we move on. Once we understand for the 1D element, we move on to 2D. So when you're talking of 1D, of course, you need to be cognizant of the Cartesian plane. Okay, we are talking, this is the x direction, this be the y direction, and this be the z direction, or the other way around. You can interchange y and z. So this one we are saying we only concerned with one direction, maybe like it's like what for a truss. You see, for a truss, we say a truss member, we simplify and we say pin jointed frame, and they can only be able to carry axial loading, either compression or tension. Okay, then we move to 2D. Now 2D, we have introduced another coordinate, the x and y. So, and in this case, we may talk of plate, shells, membrane. Why are we not talking of the slab? Slab is represented by the plate, but the thickness is small. So for a slab, the thickness becomes significant. So for this one now, the thickness here have to be considered by another coordinate. So the length is considered by one coordinate. Let's say the x, the this length is considered by another, this could be X, this could be Y, and then the Z direction could be the thickness. I hope you get it here. So when we have that direction, the thickness becomes important. Then that's when we have to introduce now the third 3D solid element. Now this one in 3D field is for stress, displacement. And you find that for our understanding in class, because we said the first objective is should be able to do manual calculation, we may dwell so much to understand the concept. We may dwell so much on the 1D and 2D element. But in real life, you find like 3D elements are typical. So 3D elements, because they are complex in terms of analysis, basically we might be using this one more on softwares. But for manual calculation, we do for 1D and 2D. Okay? All right. Now, so look at this. This is the object that we have. We have divided it into different elements. This is a 2D element, like a plate. And we are defining the nodes where the point of interconnection between the node. And at this stage, I want to introduce two terms. One is called equilibrium, and the other one is called compatibility. And what you have to realize, finite element method, for us to be able to assemble together, to bring back together what we had already separated, is that we have to assume that the nodes remains connected even after deformation, so that this node will remain connected even after we apply the load. Because what happens is that there is the load application stage, right? Then there is the analysis of individual elements. And then there's assembly, so that we can be able to analyze the whole structure. For us now to be able to assemble, we have to ensure if this was node 1 at this point, we know this is node 1. So when we separate this element, okay, and this element, I hope they resemble the same. So this is this element, this is node 1, this is node 1. So we have to bring them back together to analyze for the whole structure. And to do so, if this node and this node separated, then we might not be able to bring them back together. So the assumption is that interconnected nodes remain connected even after deformation. That's what we talk of compatibility. Okay? Common nodes remain interconnected even after deformation. Okay. Then, of course, the other one that we are going to talk about is the issue of equilibrium. Of course, that equation of static equilibrium apply for our analysis. Yeah. Of course, equilibrium, we have used it so many times, but you are going to see it in a new example. But that's just a point I said to mention, so that you don't want you not be concerned like after we have applied our load, then how do we assemble together our structure? So that's an assumption that is made. Okay. These are just examples of real analysis for finite element method. These have been done in Abacus software. The case one is where we have just a 1D. This is for the like a truss or a truss, space truss, and then each of the elements, they are just one dimension. We take it a truss, so the elements are just carrying axial loads. They can only deform axially. This is 2D, like a plate. This is 3D, of course, a solid member. Could be a formwork for a spanner without the grooves, and so on and so forth. So these are the cases of analysis when you use a software, you're going to see this. And the color coding, of course, it shows you this body or these whatever we talk of them, these structures, they have been analyzed. So that whatever it is that is shown, maybe could be the stress, maybe they are showing the stress, maybe they are showing the strain. We can now look at using the color code if it was given on the head. Of course, for this beam, for this space truss, we can see, of course, not legible because it's not necessary at this stage, but you can see the color coding showing that the red is the highest, the blue is the lowest value. So that now you can start looking at your members and see which one is experiencing high stresses, okay? And so on and so forth. You can be able to obtain values for different point or location in your structure. Now, how do we generate our FEM equations? There are two ways that we generate the equation. One of them we call of direct stiffness method. And the other one we talk of the variational methods. But for us, we stick with the direct stiffness method. It has been shown to be, for computation purposes, the direct stiffness method is more desirable because formulating the equation is simpler for most of our structural analysis problems. So what we do, we have instructional analysis. So we are saying we have two approaches that we can use. So we have the direct approaches to formulate our equations. And in direct approaches, we have two methods. We have the force or flexibility method. And then we have the displacement or the stiffness method. I was saying there is another method that you could also use, which is called the variational method. The variational method is usually employed for both structural and non-structural problems. But these direct methods or approaches, they are preferred for structural analysis. And in variational method, we can use what you call the minimum potential energy method. And or principle, we talk of energy principle. And of course, we also have the principle of virtual work. Okay. For our case, we concentrate because, as I repeat, we talked of being an introduction. We concentrate on this approach, the direct stiffness approach. And because there are two of them, we stick with this displacement method that have been shown to be quite applicable or quite useful for structural analysis problems. Just to mention what is happening here and why do we need the equation? Okay, we have, we said our complex problem or our analytical problem was constituted of partial or ordinary differential equations. Then if we introduce a boundary condition, we can be able to employ the finite element method to simplify our structure into simple algebraic equation of the form ax plus b equals c. So these are the typical equations that we use for finite element method. So the issue is, how do we generate these equations? These two approaches, force and the displacement or the direct stiffness method. For the first method, we assume that the internal forces are unknown. Forces are unknown. But for the displacement method, we assume the internal displacement u as unknown. Okay. For our case here, we can use both of them, but we said we stick with one method here. Of course, you can read further on this. But if we stick with our direct stiffness method, we look at the stages for clear understanding. We look at the stages of generating equations. The general step. One is you discretize and select the element types that you want to use. 2, you select the displacement function. 3, you define a strain displacement and stress strain constitutive relation. 4, you derive elemental stiffness metrics. 5, you assemble and introduce of boundary condition. So for unknown degrees of freedom. So for elemental stress and strains, and interpret your result. And this is what I said. Finite element method have got general steps, procedures, no matter how complex the problem is. They are the procedures that you can follow. Now, if we can go through this one by one for simple understanding. So we have our structure. And in this case now, I want to get this space. I know you have this point somewhere noted. So what we do now here, let's start with our body. Just a typical body. Okay. I'm using a general shape before we now start sticking with our regular shape, that our normal shape that you're used to, the truss, the beam, and so on. So the first thing is to discretize. If you know you're going to use the finite element method, discretize. So I've chosen to use the 2D one because we are going to see elements that have got more than one coordinate system. So you subdivide this body into different elements. So this first stage. Once you do this, right, you must decide or selection of the type of element. Okay. What element do I need to use? Remember, we have talked of 1D element. We have talked of 2D element. We have talked of 3D element. Of course, if this is a plate, then I know I'm going to use 2D element. Later on, we are going to see that in 3D element, which we call them solid elements, there are different categorization also of different solid elements, depending with the order of the polynomial. Of course, we are going to understand the interpolation that we are doing. So we are going to understand how to employ the polynomials and the order of the polynomial. But for right now, if I was talking of a truss, let this just be a typical truss. Okay, this is just a truss, normal truss. So it means there should be a straight line. It means if I discretize by subdividing, I say this is node 1, this is node 2, this is node 3, and this is a truss. So this is a single line, 1D, then I know I'm using 1D element. Number 2 is to select a displacement function. Okay, displacement function. Let me mention at this stage that finite element method using direct stiffness method, we are saying we assume displacement as unknown and force as known. We employ this expression. F is equals to K times D. Okay. Now, with this, for direct stiffness method, we assume this as the unknown. Okay. And then we assume the force are unknown, like we will be given the force applied here is 2 kilonewton, like we are given that. So we are to calculate the displacement. Let's say like this is a truss, we know the forces acting on that truss. So we are asked, maybe this is a support here, this is a support here. Maybe you are required to get what is the displacement at that node. Okay. So in that case, the direct stiffness method, or what we are saying is that because we need to get the equation, the algebraic equation that we are going to solve, which are obtained from this. Of course, remember this one you can write as F is equals to F plus or minus K delta is equals to SA0. So you can see it kind of, it will be defined in terms of simple algebraic equations that we shall be solving. Okay. Then let me just respond to this. Somebody calling me. I'm in class. Now, with that understanding, let me get this page. So you have handled the first stage. Let me get the truss. So you have handled this, discretized, and you have selected the element type. Okay. Number 2, to get the displacement function, of course, we are saying, if we consider like a bar, if we consider like a bar, single bar like that, or even a beam, and this is a load applied here, which is known, P, this is fixed, and then, of course, we know because of the applied load, the typical deformation will be like this for a cantilever. So this is the total displacement delta, or you can call it U. But let's say we want to know the displacement at this point. And the length here is L. And of course, the length up to any point that we want to talk of, because it's direction X, of course, we have to show the axis, this direction X. So we are saying this direction at any point X. So we can define the displacement at any point X will be dependent on the value X, or you may say X or X of L times something. Okay. So we are saying we have to define or to select a displacement function because finite element method is an interpolation method. Okay. Because if we subdivide our structure into bodies, let's say we define our structure into element, element 1, we have another element 2, element 3, element 4. We said the exact values will only be at the node 1, 2, 3. So any other value, if we are talking of the value of displacement at node 2 and at node 3, any other value between the two nodes is an approximation. We interpolate between the nodes. Okay, we use the exact value for between the at the node to get any other value at any other location within the node through interpolation. So this is why we are saying we define the displacement function. We are going to see more about this later on, but now you understand. So at the back of your mind, you should keep this. Know that finite element method, direct stiffness method, we are employing this equation. F is equals to the Hooke's-law, K times U. In this case, let's now start sticking with U because we are going to use displacement as U. It's just a matter of notation, okay? K times U. So you see, this is unknown. We need to get the expression, typical variation, how it's varying across the member. Now we start analyzing for individual element. K, of course, you know this is the stiffness. So we are going to obtain the stiffness for different members. Of course, I said stiffness encompasses both the material properties, that's either the Young's modulus, either the Poisson's ratio, so on, and also it encompasses the geometry, which may be given by the section modulus or the moment of inertia, so on and so forth. Okay. Now, so we have handled the stage 2 of selecting a displacement function. We are going to see this using calculation. It's quite easy, but at this stage, I just wanted you to just have a feel of the procedures or the method that we are following step by step. So the third step is now you define the strain displacement relationship and the stress strain relationship. The stress strain relationship is material characteristic, what we call the constitutive behavior. Okay. So in this case, we already know that strain is the strain is equals to change in elongation or change in deformation is a ratio. So basically what we talk about is that we know strain. First, we are defining, let me just get it here. We are defining strain displacement relationship. So this one we know from physics that if you want to get strain, we know it's changing length of the original length. And if you want to write it as a differential equation, you said is change in U over dx as a derivative, yeah? Change in U over dx. Okay, that's a strain. Then the stress, of course, we know stress is equals to strain times the Young's modulus. So you can see from this stage, we have the strain, which is here, which is expressed in terms of deformation, du, and already we have defined in step 1 a displacement function. So you can see you can be able to work it out and express stress in terms of displacement. Now, finally, or not finally, step 4, we derive the element stiffness matrix and equation. Because you see, we have this equation, the guiding equation for finite element method. The force, stiffness, displacement. And we say the force is known, displacement is unknown, K, stiffness, is known and have to be computed. And we refer to it as the stiffness. And now it's going to come into play as a stiffness matrix. It will be in matrix form. Okay. Of course, there are various methods for developing elemental stiffness matrix. And in our case, we said we adopt the direct equilibrium method. Okay. So basically now, our expression will be F is equals to KU or KD. So for an element in compact form, we have small f, because remember, capital F is for the whole structure. F is equals to capital K, and then capital D, or a big D, delta. This is for the whole structure. So for individual element, it will be F is equals to small k for an element, or elemental stiffness matrix, times small d, or U. You may be interchanging U and D. You may have to stick with U when we enter to calculation. And of course, now for the many elements, we have maybe force 1, force 2, force 3. This being on the side of the internal member forces. Stiffness matrix will be here, a rectangular matrix, and then displacement, U1, U2, U3, and so on and so forth. Okay. So F is equals to KD. We start now expressing it for each of the elements as algebraic equation. We bring them together in terms of matrix form. So once we get it for an element, then we can assemble. We come to the assembly stage. So we have obtained the elemental stiffness matrix. So we assemble, and then we introduce the boundary condition. Okay, we are going to see how the boundary condition help us. There is something we call the singularity of a stiffness matrix. In a way that a matrix doesn't have a determinant. It's not invertible. But when you introduce the boundary condition, then we remove that singularity. So that's why at the end of this course, I'm going to direct you on some revisiting that you need to do in mathematics, especially on matrices, to understand matrix operation, because you're going to be dealing with a matrix for quite a while. So once now you assemble your finite element equations for the global, we get assembly. When we assemble for individual, when we assemble or we obtain for each of these, remember we said we obtain for the elemental stiffness, then we assemble. So we get the overall. F is equals to capital K times D, right? So for our case here, when we do that, you realize we are going to get what we call the elemental stiffness matrix and the global, the capital K. This is the stiffness matrix for the overall structure. So it might end up being very large, not even to fit in your book if the structure have got many degrees of freedom. Okay. But that is the general steps that we follow, because after this now, once now you have been able to assemble and introduce the boundary condition, you just need to solve for unknown degrees of freedom. And to solve this, you are solving a set of algebraic equations. And you can use a number of methods to solve algebraic equation using matrix method. You can use the elimination method, the Gauss elimination method, or any other method that you may want to use. And you obtain the quantities D. Of course, when you solve F is equals to KD or KU, the first quantity that you're going to solve is U, which you call the primary quantities. Then from there, which are the deformation that you have obtained the primary quantities, you can go ahead and now solve for the elemental stresses and strain. These are now the derived quantities, the secondary quantities that you obtain. And of course, interpreting your results always. Okay. I hope I've been able to elaborate these steps, general cases or general way that we follow, so that when we start now doing the proper calculations, it will be very easy or quite understandable for each one of us to know what we are doing. So I'd like to add there with a short exercise. This is not to harden, but for you to visit. You need to revisit on how to handle matrices. Like when you talk of a null matrix, unity matrix, identity matrix, CDU matrix, you need to know what are these matrices. When you talk of matrix operations, you should be able to be quick and fast, to know how to add, subtract, divide, multiply, transpose, and get the inverse of the matrix. Okay, you should be able to get the determinant of matrix, because when you are solving simultaneous equation using matrix method, you need to get the determinant of matrix. And we are not just talking of 2 by 2. Maybe up to 3 by 3, somewhere like that, for hard calculation. And of course, you should now learn how to, or remind yourself, because this one you learned in first year, how to solve simultaneous equation by matrix method, so on and so forth. And if you look at in your notes, I believe either reference number 1 or 2, and now 1 or 2, I can share this note with you. I can share this book with you. There is a book. I think it's the first one, which have got a reference, an appendix, which is full of this summary of how to solve these matrices. So you can go through it quickly, and then you remind yourself. Another exercise that you need to do is that we are going to use, in this course, we are going to use Abacus as a software for learning, and the student version is available for free. Commercial version, I believe you may need to cost something over $1 million or something thereabout. But for me, I have because of the institution. So what you do we are going to use the student one so that we can be able to be in the same platform. I don't want students to go there starting to crack software. So I don't condone that. So you install Abacus student version in your laptop, or you can use the department computer laboratory. And then the class labs, I have shared with you the assignment. I've shared with you the assignment. That assignment, the second part, actually the first part, the question or the figure that is being referred to, it's available in the documentation. So it means you have to install the software as soon as now. So that's the introductory part of this course. Next week, we shall be looking at the matrix analysis of structures. So we'll be doing proper calculations now. And that's why I would like to urge you, before then, it's good you be acquainted or refreshed your memory with the matrix analysis of structures, this part that I have suggested. Okay. At this stage now, I'm looking at the chat area to see whether there's any question that somebody may want to ask. Okay. Because I want to end, we have about 4 minutes. I want to release you to go to the other class. But I would like to do so before I give you a chance to ask a question. If any one of you have got a question they would like to ask in live, then I would like to give them that opportunity. So I do so by sharing. I want to share with the class lab. So class lab, you cannot share this. You can see the issue of bombing. So you can only share this link with the group, with your group only. Don't share it outside the group. So I have given you the link. If you have a live question that you like to ask now in the next 4 minutes, you can call in. If you have any question that you like to ask in the chat that you didn't understand, you can ask, we clarify. And with that, I believe we should be able to say, oh, I stopped sharing. I was exiting the. Any question? Either in the chat or calling? Class reps, I have shared the link for Zoom. If somebody can call in live, we can be able to hear any question that they may have. So make sure you leave your registration number here, because this is where we take our attendance. Maybe next week, I don't know, we may try next week or the other week. We'll see. One of the class we come physical, we see how we break the two. Of course, the challenge with the physical is that getting a room, the room that we have been allocated, the ELB 212, it can't even handle 60, because unless they remove those benches. So, and I was saying that we have 3 classes might be tedious for me. We usually like having 2 classes. But basically, we are going to have either through tutorial or through one of the lessons, we are going to have a physical class. All right, I'm waiting for any question. Our class is over. I'm waiting for any question, comment. Yeah, I can see Mother Makori. Martha Makori, any question? Martha Makori. Who else? I can see John. You only join the link, eh? You only join the link if you want to have a question. If no question, no need to join. And you are not going to have a chat like when others are not around. Yes? So the question, if you're asking, you ask when it's live so that even the other people can benefit. Eh? Okay? Okay. It seems the people joining, they are not asking a question. Eh? It seems we are comfortable. All right. Mother, any question? Mwania Varare? Okay. All right. Thank you, everyone. Thank you for your attendance. Let's keep studying. Let's keep learning. Let's keep engaging one another. My hope is that by the time you are ending this course, you should have granted some, grasped some new concept that are going to last a lifetime. Okay, because I believe that learning is what remains after you are done with your schooling system. Like things we learned 10 years ago when I was an undergraduate. So whatever now I can remember, because I'll not be referring to books always. Even if not everything, that's what now we talk of the learning, the knowledge. Okay, so I believe is that apart from studying, my focus is not on passing this exam. And that's why you'll find like my exams are so repetitive. Like if you go through the past 3 exams, you find them in the channel, in the YouTube, they find them in some website hosted, because I don't believe in so much in the exam per se, like you are learning to pass, but you are learning so that you can get some concept that you can use when you are out there. When you have your certificate, you're out there, you can be able to understand what is happening when I use software. All right. So I'm going to add this because I can see nobody is asking a question, and it's past 10. So I'm going to stop there. Wish you well as you approach the weekend. We meet next week, same time. Class, let's make sure you share all the information I give. I have shared the assignment and the deadline for submission. I have shared this note, but my notes are outlines because I continue updating. Like you may find like the notes you have, the outline, there are points that you may need to be noting. You may have to note some points that are not there when I updated the notes, because I might even be updating them this morning. Okay. And you may find like in a PowerPoint that I'm sharing, not all information is included. So there's always that balance. So in class, always have your pen, be noting what we are saying. So I can see people joining, but maybe you did not understand. The purpose of joining was to ask question. If there's no question, no need to join. Okay. All right. Okay. That's it for today. Next week. Bye-bye.